Hello students, welcome back. Let's resume the proof of theorem 4.1. Theorem 4.1 is this: the equivalence between row expansion and the column expansion. So the first summation is this one. Look at the first row and then take all those entries A11, A12, A13, A14 with alternating signs, plus minus, plus minus, plus minus, along with those deleted matrices, capital A11, capital A12, and so on. This is the definition of the determinants. Now what we're going to prove is that's equivalent to the second expression that's basically on the expression about the column. A11, A21, A31, A41 as color-coded in blue with plus minus alternating signs, and then the deleted matrices A11, A21, A31, and so on. Now, we did some preparation for that. Deleted matrices of second generation. If we count those K and L from the original matrix, then Aij KL is equal to AKL Aij, and it is important to count them from the original matrix. If you don't, then they are not the same. We went through all these in the previous video. And then let's go to the inductive proof. The base case n equals to 2, we already did. So let's go over to inductive proof. Let's assume all these are true for the determinants of order n-1. So this and that are the same for all determinants of order n-1. All right. And then let's go over to this, which is the definition of the determinant for order n. And then we'll work those out, and we're going to prove that this is equal to that. Now, look at the first term. These two are the same. That's because whether you use first row or first column, A11 entry is the same. So this is the same, and then the deleted matrix, that part is the same. So the first term is all set. How about the other terms? Determinant of A12, determinant of A13, and so on. Well, we need some work. And let's begin working. So, determinant of A12, you can use the inductive hypothesis and expand it with respect to the column. And that's what this is. Here's a little further explanation. Here's determinant A12. So A12, take this out and that out. What's left is the deleted matrix A12. And then let's go to the column. First column. This is first entry because the first row is gone. Next entry, next entry, next entry through the columns. So A21, and then delete, delete. What's left will be this deleted matrix right over here. Next is this A13, delete, delete, and what's left will be this deleted matrix. And then A41, delete, delete, and what's left will be this deleted matrix here. So what did he do here? We followed through the column. And can we do it? Yes, because A12 is order n-1. So the inductive hypothesis works. Still having a little bit hard time? Okay, let's do it again. Let's look at this A13. And that's equivalent to this. How does that work? Well, here's A13. Original matrix and first row. Third column gone. Okay, so what's left is A13. And then we're going to focus upon the column. A21, A31, A41, A51, and so on. Can we do it? Yes, we can because of the inductive hypothesis. This A13 is deleted matrix, so it has order n-1. So by inductive hypothesis, we can do it. So get A21, delete this row, delete that column, and what's left will be this deleted matrix, A1321. Next, delete this, A13, these, and we're going to get that. And then the next one, A41, and then delete 4th first, and then this is what we get, and so on and so forth with plus minus, and so on. That is the same as the determinant of A13 using the inductive hypothesis following the column. Similar for this, similar for that, and so on. Okay, all right. Now, let's take some rearrangement. Please note that A21 is common, 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 common. So take A21 out. A12 times this, A13 times that, A14 times that, etc. And the result is this. Likewise, please note that A13 is common. This, this, this. So take it out, and then A12, A13, A14, A15, and those deleted matrices, they're all coming here. Make sense? We are taking appropriate rearrangement of all these additions, and then of course the signs follow. We can do it because this is not an infinite sum. We're talking about n by n matrix, so everything is finite. No problem about rearrangement. Now, from this rearrangement, let's go back to step 1 and then switch the order. That's what we get. A1221, A1321, A1421, they're all changed into A2112, A2113, A2114. How about the next? A1231, A1331, A1431, change all those to A3112, A3113, A3114, and so on. We went through this switching, changing the order thoroughly in step 1 in the previous video, so let's not worry too much about it. So these became those, so we are up here. The final step. Please note that this whole thing is the determinant of A21. This whole thing is a determinant of A21. This whole thing is a determinant of A31, and so on. So all these are determinants of the deleted matrices according to those columns. So we got precisely what we wanted. Let's see. Can I put those in the same viewing window? Maybe not. So let me just copy and paste this. You see? This and that exactly the same. So we got what we wanted. Of course, does everybody understand why this is equal to determinant of A21 and this is equal to determinant of A31 and so on? In case you didn't understand, let's go. So let's begin from A21, and then that's this matrix. A21 is here. Delete second row, delete first row, okay. And then in order to calculate the determinant of this n-1 by n-1 matrix, let's focus upon the first row as usual. A12, A13, A14, A15 with plus minus, plus minus. For A12, we have it here. First row out, this column. First column, if you look at it from the deleted matrix, but second column, if you count it from the original matrix, that's gone. And what's left is this deleted matrix here. Next entry, A13. So take that. First row out, third column out. Actually, if you count from the deleted matrix, it's a second column, but from the original matrix, this is third column. What's left will be this deleted matrix here. And then we go to the next one, A14, take this and delete. What's left is this with plus minus plus minus plus minus. Now it's clear. This whole thing is determinant of A21. Is everybody getting it? In case you didn't get it, okay, let's do it again. Let's look at the next one. This is A31. So this and that gone. And then let's calculate the determinant using the top row. A21, A31, A14, A15. Excuse me. A12, A13, A14, A15 with plus minus and so on. A12, take the first row out, take the first column out if you count from this deleted matrix, but from the original it's second column. What's left is this deleted matrix of second generation. Next, A13, first row out and this column out. What's left is this. And here, A14, first row out, this column out. What's left is this. With plus minus and so on. So this is a determinant of A31. And same thing. And that's precisely what we wanted. So determinant of A, which we started like this, with some multiple winding steps, in the end we got this. So that completes the proof. Now, does everybody recall that I said this proof was in completely different dimension? Well, do you appreciate what I just said? Anyway, alright, we got it done. And let's think about how to use it. Row-column equivalence. Well, okay, let's go here. And we use first row to define the determinant. But we can do the first column to do the same. So row-column, what's the difference? In terms of determinant computation, no difference. So all the properties, multilinear, alternating, those apply for rows as well as columns. So row-column equivalence. Another observation, determinant of A and determinant of A transpose are the same because transpose, what is it? Row goes to column goes to row. But then again, as far as determinants are concerned, row, column make no difference. So we have to have same determinant. Another thing, elementary row operation versus elementary column operation. Well, if you look at elementary row operation, we have three types of elementary row operation. Multiplying a certain constant C to entire row, highlighted in red, and switching two rows, ith row and jth rows, and multiplying a certain constant C to one row and adding it to another. There are three types of elementary row operations. Likewise, we have three corresponding elementary column operations. Look at the column here. Multiplying entire column by C, that's a multilinearity, so you can take C out. So if you do this elementary column or row operation, multiply by C to the determinant. How about switching? That's the alternating property, so determinant becomes negative. Whether you switch two columns or switch two rows, determinant becomes negative. How about the third? Multiply a certain number to a certain row and add it to another, or likewise, multiply a certain number to the entire column and add it to another column. According to my claim, the determinant should stay the same, and let's check. Use multilinearity to separate this linear combination. AI is here, C times AJ go there. And then look at the second determinant. We have two identical columns here and there. So this whole thing is 0, so this entire thing is just adding 0, so no change, it drops out, and we have the original matrix here. So the conclusion, this elementary column operation, and equivalently speaking, this elementary row operation down here, will not change anything to the determinants. So those are the effects of elementary operations to determinants. Multiply by C, switching, and then multiplying something and adding to another. Okay, we are almost done, and Finally, let's go to theorem 4.3, general determinant formula. We did for first row versus first column, but let's do it for ith row and jth column. How do we prove? Well, here's the proof. And what we're going to do is to use the alternating property multiple times to move jth column, to the first column and then apply theorem 4.1. Let's see how it goes. Switch these two, j minus 1 and j, and switching gives me negative. And then switch again, j minus 1 and j minus 2. J and j minus 2. And this switching gives me another negative. Switch again and again and again all the way until the last one, aj comes up front. So we get the difference, j minus 1 steps. Now I can apply theorem 4.1 because this is now the first column. So we have this summation. And here I have aij, where I is going from 1, 2, 3, 4, 5, 6 all the way to n. And that's because that's the first column. And we have this sign, and the only thing that I have to do is consolidate this negative 1 to the j minus first power into this. And that gives me negative 1 to the I plus j power, as you can see here. And that proves the general computation formula for determinant for arbitrary column, jth column. And then we can do exactly the same thing to the rows and conclude we're going to get this formula as well. Ith row, or you can use transpose to do that, but it's better to use row-column equivalence in my opinion. By the way, let me remind you of this illustration. Previously we did like this. Any ith row we can do it, in this particular case, fourth row. And any jth column we can do it, but in this particular case, third column. And then these were the general formulae for summation notation. And we just proved everything. Alright, let's go back to section 4. And we did everything, but there are two things that we didn't do yet. This one, theorem 4.5. Determinant of the product is product of the determinant. And this is going to be a huge mess. And we're going to do it in a separate video. And this is even harder. Next, uniqueness. Oh boy, this is in still different dimension, but we'll have to do it anyway, so let's go ahead and do that. And that, by the way, is related to this final topic that we skipped from determinants of order 2, the uniqueness for determinants of order 2. They're all related. And did I say different dimension? Still different dimension? You'll see what I mean when I start it. Okay, let's stop here. See you soon.